when we have an object that's hanging on a rope, like we have here with the safe, that object has a weight. It has a force downward due to gravity. And if the rope is holding that object up, then that rope has to apply a force upward. And that upward force, that force that acts along the rope, is called a tension. When you have a rope that has a force being applied to it, in this case gravity, that rope is said to be under tension, meaning that it is taut, it's pulled tightly, and there's a force being transmitted along that rope, as opposed to a rope being slack, where there's no force being applied, and the rope is just laying there. We talked a little bit before about an atomic level model of tension, basically where we think of the molecules that make up the rope as a bunch of little masses, little point masses that are connected by springs. That models the molecular bonds that exist between successive molecules within the rope. And these molecules, these chemical bonds, act like springs. And so if you have a stretched spring, that stretched spring will pull inward on either end. And that's what we have happening within the rope. We have billions and billions of these tiny springs. Each little spring is pulling inward. As it's stretched, it's trying to pull itself back into its natural or desired length. When we have billions and billions of these stretched molecular strings, all of those together are what give us this idea of tension. But the same way that each individual spring will pull towards the center, if we add up all of the springs, then our tension will pull equally in both directions. It will pull inwards in both directions, meaning that if we have a rope here with the tension pulling up, the tension on the other end would have to also be pulling in towards the middle as well. We'll see an example about how that's the case and why that's the case. In this situation, we have two students. In one situation, the one student is pulling on a rope that's connected to a wall. In the other case, we have two different students that are pulling against each other on a rope in a tug-of-war situation. In both cases, the students are all pulling with 100 newtons. And we want to know what that does to the rope, how the rope responds to these different forces being applied to that rope. The way we should look at it is in terms of the rope itself. The rope is at equilibrium because the rope is not moving. It's staying still as the student pulls on it and as it's anchored to the wall. And so if the rope is in equilibrium, the net force on the rope has to be zero, because there can't be any acceleration, or else the rope would be moving. So we look at what forces are being applied. If the student is applying a force on the rope has to be pulling back on the student. But if the rope is in equilibrium, if there's a force on one end, there has to be a force on the other end of the wall, canceling it out. So in that case, if there's a force at the far end, a force of the wall on the rope as well, then the rope has to put a force on the wall that is equal to that 100 newtons to balance out all of the other forces acting in the system. And thus, the amount of force that the rope pulls in on one end has to be the same as the amount of force the rope pulls in at the other end, so that the rope can stay in equilibrium. The same is true whether it's a wall or another student. In the same situation, if one student pulls with 100 newtons, they are going to be pulling on the rope, and so the rope will pull back on them with that 100 newtons. but the rope is again in equilibrium. And so you have to have a total 100 newtons acting on the rope, meaning that the other student would also feel the 100 newtons, which we know to be the case. We know that she's applying 100 newtons as well. And so in this situation, you get 100 newtons acting on either side. So the tension of the rope is considered to be 100 newtons. The tension is the amount of force that the rope carries, the net force that the rope transmits between its ends. In this case, we're seeing that the other student is applying 100 newtons, and so she's feeling that. In this case, this 100 newtons shows up in the wall, and so if the rope is anchored into the wall, this is the force that's acting on that anchor. You can imagine if it's a screw or a bolt into the wall, if it's not secured well enough, you could pull hard enough and pull that anchor right out of the wall. The way you would pull that anchor out of the wall would be through that transmitted force via the rope. Previously, we were looking at the tension in a rope, and we were looking at the forces being applied to that rope, and we said that that was mass times acceleration, and we said that those situations with a tug of war, the acceleration was zero, and that's why the forces had to balance out. That's not always the case, however. Sometimes you'll have an acceleration, you'll have a system where you'll have a couple blocks, a couple objects that are connected by a rope, and you have an external force being applied to them. And in that situation, this external force would accelerate the entire system, similarly to what we've seen in the past, where in the previous lesson we saw a hand applying external force and accelerating a pair of blocks that were pushing against each other. This is a similar situation, except that force is transmitted via the rope. And what happens typically is the rope is often much less, has much less mass than the objects it connects. In this case, we assume a massless string. What this means basically is the simplifying assumption that if we apply an external force on B, B is going to apply a force on the string as B moves to the right, and the string will apply a force back on B as well. As the string moves, that force, that string will have a force on A, and A will have a force on the string. In this situation, the string is moving to the right with the rest of the system, and so the string would have a sum of forces equals mass times acceleration. And if the string is accelerating, that means that this is a positive value. The sum of the forces here, which would be the force of B on the string minus the force of A on the string, this would not be zero, and these two terms would not be equal to each other, because some of that force goes into accelerating the string itself, bringing that along with the rest of the system. However, because that complicates the system and because the string is so small, it doesn't really help a whole lot. And so what we assume is that the mass of the string equals zero. And if that's the case, then that means that these two subtracted end up equaling zero anyway. And that allows us to say that the forces on either end of the string, the tension forces pulling inward, should stay constant, should stay equal to each other, even as the system accelerates in one direction. When we make this simplifying assumption of the massless string, we can really take the string itself out of the situation. If it's massless, it's not going to contribute to the motion of our object. And so what we end up happening is we have an external force, we have a string connecting these two blocks, but because the string itself isn't really contributing other than transmitting that force, we can treat it as if there's an action-reaction pair where the block A is pulling on block B, and block B is pulling back on block A. In real life, we know block B is pulling on the string is pulling on A, and A is pulling on the string, and there's a much more complicated system, but by assuming that the mass of the string is much less than the blocks, we can simplify that a whole lot, and because the string is so much smaller than the block, we really have a pretty small loss in accuracy for simplifying the system this much. And what we can end up doing, if we treat these as an action-reaction pair, is that we see that they have to have the same magnitude, seeing that the tension of the rope is transmitting that force all the way through, and one is the negative of the other, meaning that the string is pulling in opposite directions. Because whenever you have a string, the tension force, always pulls towards the middle of the string. And it pulls away from whatever objects are at the ends, and it always pulls them towards the middle of the string. It can never push outward, because then that would be the rope somehow pushing you outward. So we transmit the force without changing the magnitude, and we assume that strings and ropes are massless unless we tell you otherwise. When we get to strings having significant mass, we'll see that they can complicate the system a fair amount, and so that's why for right now we want to assume massless strings. This is another situation where we have two blocks that are connected by a rope, but not only are they connected by a rope, they're also connected by a pulley there. In this situation, block B will tend to fall downwards. As it falls, it will drag A across the table. So there will be an acceleration downwards and an acceleration to the right for block A. We've already said that the string should be assumed to be massless because the string will be much less than the blocks, and because that simplifies our calculations greatly. However, we also have to assume that the pulley is massless as well. If the pulley was not massless, then if it had some mass to it, it would take a certain amount of force to get it spinning. And as the blocks accelerate, the pulley would have to spin faster and faster as the rope goes by faster. And so that would take force to get the pulley spinning in that situation. And that force would come from the rope and would take away from the acceleration of the blocks. We'll see in a few chapters how to deal with a massive pulley, but for right now we're going to ignore that mass. Technically, the pulley, as it spins, should have some sort of rolling friction as well between the pulley and its axle, or between the rope and the pulley. But we are assuming no friction for the pulley as well, again, just to simplify that. And if that's the case, if we go along with these simplifying assumptions, then the magnitude of the tension acting on A has to equal the magnitude of the tension acting on B. And so if you make free body diagrams for block A, a free body diagram for block B, even though these two tensions point in different directions, their magnitudes are still equal because they're connected to the same rope. That same rope is being stretched out, and those little tiny springs, chemical bonds within the rope between the molecules, are transmitting that force along the entire length, spreading out that force along the entire length of the rope, and thus you get the same tension at either end of the rope. We see again the magnitudes of the two forces are the same, and so we can draw them in a free body diagram with the same magnitude. It's an important point, though, the two forces themselves, not their magnitudes, but the forces themselves, they act as if they're an action-reaction pair. But technically they're not really, because they're not opposite in direction. The tension force gets turned by the pulley, and so it changes the direction. But they act as if they're a action-reaction pair because of they both interact with the same rope. To recap ropes and pulleys, we are assuming that we have massless ropes and massless, frictionless pulleys. We'll mention that so as to be technically correct, but that's the safe assumption that we'll have unless we're specifically told otherwise. When you have a force that pulls on one end of the rope, the tension is equal in magnitude to the pulling force. So if you're pulling on one end of the rope, the amount of tension on the rope is that amount, and that amount of tension is transmitted through the rest of the rope. If you have two objects connected by a rope, the tension is the same at both ends. So the rope is transmitting the same amount of tension along its entire length. And if a rope passes over a pulley, the tension is unaffected. So the pulleys will change the direction of the rope, they'll change the direction of the tension, but they won't actually change the value of the tension.